Hello, testing. Okay, so hold on. Hello, everyone. Can you hear me? Okay, so I'm going to be learning physics again. Hold on. Let me just change to full screen. Right, so this is the OpenStax physics textbook. I read about units and measurement. I read about vectors. This stream I will be reading about motion along a straight line. And I should open up the answer key as well. Also, I have Desmos open for calculations. This is chapter 3. Oops. Never mind. Our universe is full of objects in motion, from the stars, planets, and galaxies to the motion of people and animals. A full treatment of kinematics. Is that how you pronounce it? Um, Kinematics considers motion in two or and three dimensions. For now, we will discuss motion in one dimension, which provides us with tools necessary to study multidimensional motion. A good example of an object undergoing multidimensional motion is the maglev, magnetic levitation train, depicted at the beginning of this chapter. As it travels from Tokyo to Kyoto, so this train, it is at different positions along the track at various times in its journey, and therefore has displacement or changes in changes in position. It also has variety of velocities here. Okay, next chapter. Position, placement, and average velocity. Hold on. Sorry, I'm just checking something. So, to describe motion of an object, you must be able to describe its position where it is at any particular time. More precisely, we need to specify its motion relative to a convenient frame of reference. The frame of reference is an arbitrary set of axes from which the position or an object of an and motion of an object are described. So, if an object moves relative to a frame of reference, for example, if a professor moves to the right relative to the whiteboard, the object's position changes. This change in position is called displacement. The word displacement implies that an object has moved or has been displaced. Although position is the numerical value of x along a straight line where an object might be located, displacement gives the change in position along this line. Since displacement indicates direction, it is a vector and can either be positive or negative. The displacement is the change in position of an object. Xf is the final and x naught is the zero. Objects in motion can have a series of displacements. In the previous example of the pacing professor, the individual displacements are 2 meters and negative 4 meters, giving the total displacement of negative 2 meters. We define total displacement as the sum of individual displacement. Express this mathematically with the equation. So total displacement is the sum of all the individual displacements. For each position xi, we assign a particular time t. The details of the motion at each instant are not important. The rate is usually expressed as the average velocity, v with a dash. This vector quantity is simply the total displacement between 2 points divided by the time taken to travel between them. The time taken to travel between 2 points is called the elapsed time. If x1 and x2 are positions of an object at times t1 and t2 respectively, then average velocity is the change in x over the change in time. So this is example 3.1. Example 3.1. Jill sets out from her home to deliver flyers for her yahtzee. What is the jet's total displacement to the point where she stops? Traveling due east along a straight line with houses. At zero point 0.5 kilometers and 9 minutes later, she runs out of flyers and has to retrace her step back to her house to get more. This takes an additional 9 minutes. After picking up more flies, she sets out again on the same path, continuing where she left off and ends up 1 kilometer from her house. Third leg of her trip takes 15 minutes. At this point, she turns back towards her house, heading west. After 1.75 kilometers and 25 minutes, she stops to rest. So, what is her total displacement? So he goes 0.5 kilometers, right? Here and then back. And then she sets out again on the same path, continuing where she left off, and ends up 1 kilometer away, and then goes back 1.75 kilometers. So the total displacement would be 0.75 kilometers, right? So these two cancel out. 1 kilometer, we have 1 kilometer back and then 0.75 kilometer. So the total displacement is 0.75. What is the magnitude of the final displacement? 0.5 plus 0.5, which is 1, plus 1, which is 2, plus 1.75, which is 3.75. What is the average velocity during her entire trip? So 9 minutes plus 9 minutes. She starts out again on the continuing where she left off. So this takes 15 minutes and 25 minutes. 9 plus 9 plus 15 plus 25. Plus 9 plus 15 plus 25 is 58 minutes. Average velocity. 0.75 divided by 58, right? So the average of all of this is 0.0129 kilometers per minute. What is the total distance traveled? The total distance is 3.75. So what do they mean by this? What is the magnitude of the final displacement? The magnitude is 1.75, right? Make a graph of position versus time. Yeah. Um, Is the speed consistent throughout? So we have 0.75. Average velocity is, sorry, total displacement is minus 0.75. The magnitude of the total displacement is 0.75. I should have said a minus. Average velocity, what I calculated, 0.013. The total is 3.75. Position is like this. Instantaneous velocity and speed. So the instantaneous velocity is the derivative of the position divided by time. I've already studied calculus, so I'm gonna rush through this. So the derivative is the gives the slope of the tangent. So the instantaneous change in x divided by the instantaneous change in y. This would give the tangent line. Given the position versus time graph of 3.7, find the velocity versus time graph. So the position is increases like this. So what is this? 0.5, wait, 0.4 divided by 0.4. So this is 1, right? So we have 1 meter per second. Should write it here. We have exactly graph 1 meter per second. And then 0 meters per second after 0.5. And then 8, 9. We have, what is this? Is this negative 1? It's 2 minus 0.9. 2 minus 0.9 divided by 0.5. Sorry, 0.5 divided by 2 minus. Wait, hold on. I will be back in a few minutes. Something just came up. Sorry. Hello. Sorry. Something came up. I had to go. I will cut that part of the stream in the final edit. Okay, continuing from where I last left off. So it's just my mic, okay? So it's going minus 0.5 meters in 1.1 seconds, and that's 0.4545. It's minus 0.4545. So it would be like that. Yeah. Uh, minus 0.4545. So the velocity is this, and then this. Well, they rounded it up to minus 0.5, rounded it down. In everyday language, most people use the term speed and velocity interchangeably. In physics, however, they do not have the same meaning and are distinct concepts. One major difference is that speed has no direction. That is, speed is a scalar. You can calculate the average speed by finding the total distance traveled by divided by the elapsed time. However, we can calculate the instantaneous speed from the magnitude of the instantaneous velocity. All right. I forgot to change it to full screen. So, anyways, so with this exercise, I was finding the velocity versus time. So the velocity is 1. The velocity here is 1 because it's like 0.4 meters in 0.4 seconds. And then the velocity is 0. And then the velocity is negative 4.454545. Because it's like minus 0.5 meters in 1.1 seconds. So instantaneous speed is from the magnitude of velocity. The particle moves along the x-axis at 7 meters per second, and another particle moving along the same axis at minus 7 meters per second. They have different velocities, but both have the same speed, 7 meters per second. Calculating instantaneous velocity. In calculating instantaneous velocity, we need to specify the explicit form of the position function. And if each term in the x equation has the form a t to the power of n, where a is a constant and n is an integer, this can be differentiated using the power rule to be a n. So a is a constant, yeah, a n t to the power of n minus 1. That's just derivatives. Next chapter. Average and instantaneous acceleration. The formal definition of acceleration is consistent with these notations just described, but more inclusive. Average acceleration is the rate at which velocity changes. So rate of change in velocity divided by the change in time. The term deceleration can cause confusion in our analysis because it is not a vector and it does not point to a specific direction with respect to a coordinate system. So we do not use it. Acceleration is a vector, so we must choose the appropriate sign for it chosen in our chosen coordinate system. Right. In the case of the train in figure 3.10, acceleration is in the negative direction in the chosen coordinate system. So we say the train is undergoing a negative acceleration. Because the train is slowing down, right? So velocity is still high, but acceleration is backwards. Because the velocity is decreasing. Final velocity is lower than the initial velocity. Instantaneous acceleration is the derivative of velocity with respect to time. You have the slope of the tangent line. To understand this concept, let's look at two examples. First, a simple example using figure 3.9. It is 3.9b. Figure 3. What do they mean figure 3.9b? The velocity versus time graph of example 3.4. Find acceleration graphically. This graph depicted in 3.15a, which is a straight line. A straight line. In this example, the velocity function is a straight line with a constant slope. So velocity is continuously decreasing, right? So there's a constant negative acceleration. Getting a feel of acceleration. So high speed train has 0.5 meters per second. Elevator has 2 meters per second. Wait, what? Why is high speed train 0.25? Shouldn't it be much higher? So object in a free fall without air resistance near the surface of the earth, 9.81. Motion with constant acceleration. You might guess that the greater the acceleration of, say, a car moving along a stop sign, the greater the car's displacement in a given time. But we have not developed a scientific equation that relates acceleration and displacement. In this section, we look at some convenient equations for kinematic relationships. Starting from the definitions of displacement, velocity, and acceleration, we first integrate a single object in motion called single motion body. Then we investigate the motion of two objects called two body pursuit problem. First, let us make some simplifications in notation. Taking the initial time to be zero as if time is measured with a stopwatch is a great simplification. Since time elapsed is delta t, taking t not as zero, that means delta t is t final. Right. So we have delta t, delta x, and delta v. To summarize, using the simplified notation, with the initialized time taken to be zero, we have all this. We make an important assumption that acceleration is constant. So what exactly are we trying to figure out? Motion with constant acceleration. Right. Uh, okay, I'm gonna guess what they're going to do. So they have delta t, delta x, delta v. V, let's say v minus u. So v is final velocity, x1 minus x naught. And then acceleration is constant. So the average acceleration is equal to change in velocity over change in time. And this acceleration is constant. So I will just write A A is constant. And then final minus inertial over time. Oh, the average velocity. So the graph. So velocity over time. Graph should look like this because the acceleration is constant. The average velocity is x1 minus x naught over delta t. The average velocity is also the final minus initial divided by 2. So then what? Okay, so I understand how they got this. They got this from here. And then we have like that. We got this. Average velocity is these two divided by two. And oh yeah, since acceleration is constant, acceleration is also this. So from this, so the first equation they got was from this x0 plus it with um, average velocity. The second equation is from here. So V is equal to U plus A. Forget the delta. T is the difference in time. And what else? Solving for final position for with constant acceleration. We get we have this and we have this. So they have this equation, they have 80. Yeah. We have V minus U divided by T. No, this is wrong. V minus U like that, right? V minus U, divide both sides by 2. And then we have average velocity. And then we have average velocity is also this. So this plus half AT square. No, I missed something. Wait. I missed something. This is plus U. So it's all this. This is the third equation, right? So final velocity is final position is initial position plus initial velocity times t plus half at square. We have v square is equal to u square plus 2ax minus x naught. So let me copy this. Oh, never mind. And what's the last one? They want final, initial, a, and the two of these. I'm getting confused. This is average velocity. This is also average velocity. That should be a plus. No, hold on. Wrong about this. This should be a minus. Me erase all of this as I getting confused. Right. First, let's start with defining the terms. So we have t, which is time. We have v, final, u, initial, final, initial. Uh, net time, final velocity, initial velocity, final position, initial position, and then acceleration, constant acceleration. And then we have this average velocity. Velocity. Now, first of all, average velocity, since the acceleration is constant, right? The velocity would look like this. V and then U. Or it would be easier if I imagine in this is the initial velocity. This is the final velocity. and the acceleration is constant. No, no, no. This is u. This is v. This is t. So average velocity is v plus u over t. Average velocity by definition is also the change in position over time. Acceleration is change in velocity over time. So our first equation is making x1 the subject. X1 is equal to this is our first one. Let me box it. Second equation is the next one. It's this, which is just rearranging this. So the second equation is this rearranged. So P V acceleration is V minus U. Change in velocity over time. Velocity is acceleration plus U over T. No, T goes here, U goes here. What's the next equation? Yeah, this we have putting, wait, what? They adding V naught to each side of this equation and dividing by 2. Okay, so from this we have V plus U 2U plus AT, and then divide by 2, and then the average velocity is also x1 minus x naught. And then we have bring t to the other side plus ut half at square. This is the third equation. Then lastly, we have this from So they got rid of t, right? T is equal to v minus u over a from this. Let's just put this here. T is equal to v minus u over a. And substituting this and this into this. I think it's better if I write here. And we have v plus u over 2 equals to substitute this into this. We have x1, x naught over a. Like that. Nope, it's the other way around. So bring this here. V square minus u square gives you 2a x naught. This is our other equation. Putting the equations together, we have all this. I keep forgetting these ones so many times. Okay, let's try to solve this question. On dry concrete, a car accelerates opposite to the motion at the rate of 7 meters per second square. Whereas on wet concrete, it can accelerate opposite to the motion at only 5 meters per second square. Find the distance necessary to stop a car moving at 30 meters per second on dry concrete and wet concrete. Repeat both calculations and find the displacement from the point where the driver sees the traffic light turn red, taking into account the reaction of 0.5 seconds to get their foot on the brake. Okay, on dry concrete. So let's try A first. Dry concrete. On dry concrete, a car accelerates opposite to the motion at the rate of 70 meters per second square. So 3.10a, example 3.10a. So acceleration, this looks like backwards 7 meters per second. Okay. Find the distances necessary to stop a car moving at 30 meters per second. So the velocity is 30 meters per second. Velocity is 30 meters per second. A car can accelerate opposite to the motion at the rate of 7 meters per second. Find the distances necessary to stop a car moving. Okay, so what they're asking is that we start with 30 meters per second, we end with 0, the acceleration is constant, the acceleration is constant, and we need to find delta x. Well, displacement in some, like when I learned it in A levels, it was represented as S is the change in displacement. Find the distances necessary to stop a car moving. So the minimum distance required. So v square minus u square. So S is equal to v square minus u square over 2a. Yeah. So the change in position is v square minus u square over 2a. This is 0. So it's 30 square over 2 times 7. So 30 square over minus 14. This is minus meters per second square. So is this correct? Is it negative displacement in the opposite direction? Minus 52.94 meters. But is it, if it's negative, so it should be minus 52? No, that's where I'm wrong. The initial is 30 meters per second. Final is 0. So this is positive. 0 minus 30 square over minus 2 times 7 gives 52.94 meters. So it has to be at least these many. So the distance has to be this much. So the car has to be at least that much away. And we need to do this again for wet concrete. Let me see if it's correct for dry concrete. They got 64.3. 30. Oh, wait. It's minus 14. 64.3. $64.3. Should the answer be on one significant digit? Because in units and measurement, no, wait, 1, 2, and 3. 1, 2, and 3. It's 3 significant figures. Yeah, so the final answer should be in 3 significant figures. Similar, use the same equation on wet concrete. Repeat both the calculation, find the displacement from the point where the driver sees the traffic light turn red taking into account the reaction time of 0.5 seconds to get their foot on the brake. Wait, I don't understand the last one. The driver reacts, the stopping distance is the same it is in A and B for dry and wet concrete. So to answer this question, we need to calculate how far the car travels during the reaction time. Then add that to the stopping time. So we have 64.3 meters. But because of the reaction time, it's now going to be 79.3. The displacement found in this example seem reasonable for stopping a fast moving car. Okay. Uh, how long is it left? Okay. Suppose a car merges into a freeway traffic on a 200-meter long ramp. If its initial velocity is 10 meters per second and it accelerates at 2 meters per second square, how long does it take the car to travel 200 meter up the ramp? 3.11. Suppose a car merges into a freeway traffic on a 200-meter long ramp. Its initial velocity 10 meters per second. It accelerates at 2 meters per second. How long does it take the car to travel up the 200-meter ramp? He gave us U and they gave us A. We need to find time t. The acceleration is constant. Acceleration is v minus u over t. But the thing is, they didn't tell us the final velocity. They did give us s, which is 200. S is equal to ut plus half a t squared. So the acceleration is constant. The initial is this, and with if the initial velocity is 10 meters, if it keeps accelerating, if the acceleration is constant at 2, then how long it would take to cover 200 meters? Then t plus t square. To use the quadratic formula, can't it be solved 10 plus t. Never mind, I will use the quadratic formula. T is equal to, actually, t square minus 10 t plus 200, 0. T is equal to minus b plus minus b square minus 4 times a times c over 2a. Hey, this is not possible. Minus b plus minus root b square minus 4 times a times c. Did I? Oh, it's minus, right? So this is plus. E is equal to minus b plus minus root b square minus 4 times a times c. So root 900, which is root 300. Root 9, I will just. So minus 30 it's not minus 10, it's plus 10. Plus 10, and we have 900, negative 10, and 20. But the correct answer is only 20 because time cannot be negative. It says 10 here. I did a mistake. How far? Okay, I got this correct. Plus 10. So they did negative 200 minus b plus minus. Oh, 2a. So it's negative 2. So this is plus, this is negative. So 10 meters per second is correct. The most remarkable and unexpected fact about falling objects is that if air resistance and friction are negligible, then in a given location, all objects fall towards the center of the earth with the same constant acceleration independent of their mass. I mean, it changes with distance. It's not exactly constant. But over small distances, it barely makes a difference. This experimentally determined fact is unexpected because we are so accustomed to the effect of air resistance and friction that we expect light objects to fall slower than heavy ones. Until Galileo proved otherwise, people believed that heavier objects have a greater acceleration in free fall. We now know that it is not the case. In the absence of air resistance, heavy objects arrive at the ground at the same time as lighter objects when dropped from the same height. In the real world, air resistance can cause a lighter object to fall slower than a heavy object of the same size. A tennis ball reaches the ground after a baseball dropped at the same time. Air resistance opposes the motion of an object through the air and friction between objects, such as between clothes and a laundry chute, or between a stone and a pool into which it is dropped. Also opposes motion between them. For the ideal situation of these first few chapters, an object falling without a resistance or friction is defined to be in free fall. The force of gravity causes objects to fall towards the center of the earth. The acceleration of free falling objects is therefore called acceleration due to gravity. Acceleration due to gravity is constant, which means we can apply the kinematic equations to any falling object where a resistance and friction are negligible. This opens to us a broad class of interesting situations. So acceleration is 9.81. It is so acceleration due to gravity is so important that its magnitude is given its own symbol, g. It is constant at any given location on Earth and has the average value g is equal to 9.81. Although g varies from 9.78 to 9.83 depending on the latitude, altitude, underlying geographical formations, and local topography. Let's use an average value of 9.8 rounded to two significant figures in this text unless specified otherwise. Neglecting these effects on the value of g as a result of position on Earth's surface, as well as effects resulting from Earth rotation, we take the direction of acceleration due to gravity to be downwards. In fact, its direction defines what we call vertical. Note that whether acceleration A in the I don't know why this word confuses me. Kinematic. Kinematic equations has the value plus g or minus g depending on how we define a coordinate system. If we define the upward direction as positive, then A is equal to minus g equal to minus 9.8. If we define the downward direction as positive, then A is equal to plus 9.8. We assume here that acceleration equals minus g. So now we have the positive direction upwards. So with our Lewis equations, so B is equal to U plus AT. But positive is upwards for a falling object. Instead of A, we have minus G. G is in the downward direction. We also have S is equal to UT plus minus GT square over 2. And then we have minus G over here. Or these are all questions. I'll just do one of them. Figure 3.27 shows the positions of a ball at 1 second intervals with an initial velocity of 4.9 meters per second downwards that is thrown from the top of the 98-meter high building. How much time elapses before the ball reaches the ground, and what is the velocity when it arrives at the ground? So, shows the position of a ball at 1 second intervals, then initial velocity of 4.9 meters per second. That is thrown from the top of a 98-meter high building. How much time elapses before the ball reaches the ground? So yes, 0, 1. Okay. What is the velocity when it arrives at the ground? So this is example 3.14. We have a ball going downwards. Initial velocity is 0. A is minus 9.81 meters per second square. Sorry, initial is 4.9. 4.9. And then S is 98. 98-meter high building. And they expect us to use two significant figures, right? So they want, what do they want? They want the time first and then the final velocity second. So S is equal to ut plus half at square. They want the time. S is 98, 4.9 t plus it actually is a minus. Minus 9.8 divided by 2. 4.9. T square. T square minus 4.9 t plus 98 is 0 minus b plus minus b square. Hold on a minute. Actually, I can divide both sides by 4.9, right? Wouldn't that be easier? So I have hold on, let me just make sure. 98 divided by 4.5 is 20. We have 10 t square minus t plus 20. 0. Minus b plus minus b square minus 4 times a times c. Minus 4 times a is 40 times c, 800. But this shouldn't be possible. I'm making a mistake somewhere. The negative, this is negative direction. So this is minus 4.9. Minus 4.9. So this becomes positive. But that doesn't make a difference. 98 meters displacement. It would just be easier to treat them. So let's treat the downward direction as positive. So we have this, and then we have this, and then we have this. So minus p plus minus p square minus 4 times a times c over 2a 20. You have 900. Square root is 30, right? So 31 over 2, 15.5 seconds. And is this correct so far? T square plus T minus 20. Ninety-eight, 4.9, and 9.8. So 98, 4.9, and 9 minus plus. Did they do a mistake? Wait, this doesn't. 98 meters divided by 49 is 20. 9.8 meters per second divided by 49. Sorry, divided by 4.9 is 20, divided by 4.9 is 1. And then 4.9, this is point. This is wrong. Minus. Minus b plus minus b square. Minus 4 times a times c. So I have 81. So I have 9, right? So root 81 is 9. If it was plus 9, you would have 9 plus 1, 10. Divided by 20 would give us half. But it's not half. No. It's this. So 10 divided by 2 would give us 5. 5 seconds. This is correct. Now we have a v square plus u square. What's the simplest equation? So acceleration is change in velocity over time. Four 4.9 over 5. 9.8 times 5. And we have plus 4.9. 53.9. Why do I keep getting it wrong? Yeah, minus u times 5. This is correct, 44.1. But the thing is, You're treating the downward direction as a positive, right? If you treat the downward direction as positive, V is equal to U plus 80, 4.5 plus 5 times 9.8. Why is it 4 seconds? Hold on. 1 plus 80 is 81. Then we have plus minus 9. So 1 plus 9 divided by 2. Or we have 1 minus 9 divided by 2. Oh, it's negative 2. So it's minus 5 or 4 seconds. So the correct answer here is 4. Now it makes sense. And so if we times it by 4, we get an even worse answer. So 9.8 times 4 plus 4.9, which is 44.1 meters per second. Finding velocity and displacement from acceleration. Oh my god. Okay, so we did calculus. This should be easy for us. Let's begin with a particle with an acceleration a, which is a known function of time. Since the time derivative of velocity function is acceleration, we have derivative of v is equal to acceleration. We can take the indefinite integral of both sides, where c1 is a constant. Okay. Since this is equal to velocity, velocity is given by the integral of acceleration plus c1. Similarly, for position, we have this. We can derive the kinematic equations for a constant acceleration using these integrals. With a constant, during the integration, we find this. If the initial velocity is 0, then this, then c1 is equal to v0. Or because acceleration is constant. All right, we can derive all the other equations like this. Okay, I took like, these are the key terms. I think I will end the stream here. I wanted to do the questions, but I took a lot of time in between. Now the summary, conceptual questions. I wanted to do some of the problems. Instantaneous. Uh, Let's do this. Between t0 and t is equal to t naught, a rocket moves straight upwards with an acceleration given by a minus b t to the power of half. So this is question 79. So hold on. So a rocket, or should I? Rocket goes upwards. Acceleration is a minus b t to the power of minus t to the power of half. Um, wait, a and b are constants. If x is in meters and t is in seconds, what are the units of a and b? A is meters per second. The dimension, we write it like this, right? Meters per length square. No, it's you do length. The dimensions are written like this, right? Length over time squared. T is equal to time. This is the dimension of time. So length over time square. Dimension of A, dimension of B. T is measured in half. So T is half. So we need L over T to the power of half to cancel out with this. T to the power of half, cancel out with this, and we need 2 over here, right? So we need 8 over. No, that doesn't make sense. T to the power of 4 t to the power of 4. Let me think about this. If t to the power of half, no, this is not correct. We need it to cancel out with this, and we need t squared to remain. So it's 2.5. So the dimensions of P is in meters per second, 2.5. Dimensions of A is in length over time squared because it needs to match with A. And then B is length over time to the power of 2.5. Question 79. Meters per second square. B is equal to meters per second, 5 over 2. If the rocket starts from rest, how does the velocity vary between t0 and t is equal to t naught? So, velocity at a particular time Let me think. A minus B t to the power of half. This is a definite integral. So we are starting at 0 and t is equal to t naught. If the rock starts from rest, how does the velocity vary? A t and then from 0 to t minus b this is plus 1 t over 2 over 3 over 2. Um, so this is just at. This over here. The 0 part will cancel out and then we are left with the 2 times this divided by 3. 79, 80, 2 over 3. Yeah. But the thing is, yeah, the final velocity is t naught. So how does the velocity vary between this to this? At a particular time, the velocity would be this. And we also have the distance, which is change in velocity, the integral of velocity. Did they give the initial and final during the same time interval? Let's do t naught. So we have let's just do this. Dt minus we will bring 2 over 3 outside. A is a constant, so is B. A is a constant, I can just bring that outside. This will be two B over 3 5 over 2 5 over 2. The 0 part isn't going to have any effect. Only t naught, but the 0 will cancel out. This over here, we have p over 3 t naught 5 over 2 5 over 2. But this can be rewritten as divided by 5 times 2. So 4b times t naught to the power of 5 over 2, and then the bottom will be 50. 79, 4 over 50. Okay. I will end the stream here then. Uh, and yeah, I will see you guys in the next stream and I study the next chapter. Anyways, see you guys next time then. Bye.